Welcome to our discussion on building batteries, focusing on the manufacturing process and the critical role of Li-ion separators. We aim to understand separator materials and their design requirements. We'll explore types like polyethylene and ceramic-coated films and analyze key design parameters. These include porosity, permeability, puncture strength, tensile strength, shrinkage, and ionic insulation capability, all vital for battery performance and safety. The separator is truly the guardian of safety and performance within a battery. Its primary role is to ensure the battery's safe operation, optimal performance, and extended longevity. Functioning as a protective barrier, the separator allows lithium ions to pass freely between electrodes while strictly blocking the flow of electrons. This selective permeability is fundamental to preventing internal short circuits and enabling the electrochemical reactions necessary for energy storage and release. The separator performs two primary functions: electronic insulation and ionic conduction. For electronic insulation, it physically separates the anode and cathode, preventing direct contact and internal short circuits. Made from non-conductive materials, this is fundamental for battery safety, preventing rapid discharge, overheating, and thermal runaway. Simultaneously, it must allow free and efficient passage of lithium ions through electrolyte-filled pores, directly affecting internal resistance, power capability, and rate performance. The separator must also be chemically stable, mechanically robust, and thermally stable. Polyolefin films are common separator materials. Polyethylene, or PE, is a microporous polymer film known for its thermal shutdown mechanism around 130 degrees Celsius, offering low cost and good mechanical strength. However, it has lower high-temperature tolerance. Polypropylene, or PP, has a higher melting point around 165 degrees Celsius, providing better high-temperature dimensional stability, but lacking an inherent lower temperature shutdown. Multi-layer separators, typically PP/P/PP, combine these benefits, with PE providing low-temperature shutdown and PP offering structural integrity and higher temperature resistance, enhancing safety across a broader range. Ceramic-coated films represent another critical separator type. These consist of a polyolefin-based film coated with a thin layer of inorganic ceramic particles, such as alumina or silica, embedded in a polymer binder. Advantages include superior thermal stability, often exceeding 200 degrees Celsius, reduced thermal shrinkage, improved mechanical strength, and enhanced safety during thermal events. While they come with higher costs and a slight reduction in energy density, the ceramic layer acts as a fire retardant, high-temperature resistant barrier, crucial for high-energy density batteries in applications like electric vehicles. Porosity and permeability are critical design parameters. Porosity refers to the volume fraction of voids within the separator, typically 30 to 60%, influencing electrolyte retention and ion transport pathways. Higher porosity generally leads to lower internal resistance, but can reduce mechanical strength. Permeability measures how easily electrolyte and ions flow through the porous structure. It affects electrolyte wetting speed and ion diffusion kinetics, being crucial for initial electrolyte filling and high-rate performance. Balancing these properties is essential for optimal battery performance. Puncture strength and tensile strength are vital mechanical properties for battery separators. Puncture strength refers to the separator's resistance to penetration, crucial for preventing internal short circuits caused by dendrite growth or manufacturing defects, directly impacting battery safety. Tensile strength, on the other hand, is the material's resistance to breaking under tension. This is important during manufacturing processes and for maintaining separator integrity as electrodes expand and contract during charge and discharge cycles. Both properties ensure the physical barrier remains intact under various stresses. Thermal shrinkage is a significant safety concern for battery separators. It describes the degree to which a separator film contracts or deforms when exposed to elevated temperatures. If a separator shrinks excessively, it can expose bare electrode surfaces, leading to internal short circuits and potentially triggering thermal runaway. Solutions to minimize thermal shrinkage include selecting materials and processing methods that inherently reduce contraction, incorporating ceramic coatings for structural stability, and designing for controlled shutdown mechanisms, such as those found in polyethylene separators, to prevent uncontrolled shrinkage. Ionic insulation capability is an uncompromisable requirement for battery separators. This encompasses two aspects: electronic insulation and ionic conductivity. The separator must not conduct electrons to prevent internal short circuits. This is verified by confirming negligible electronic current flow through a dry separator. Conversely, ionic conductivity must be high for efficient battery operation. This is facilitated by a porous structure filled with electrolyte, providing clear pathways for lithium ions, and is typically measured using techniques like electrochemical impedance spectroscopy. The separator's ability to block electrons while allowing ions defines its fundamental function. In summary, the separator, though small, is mighty. Its fundamental functions are ensuring electronic insulation while facilitating ionic conduction. Material types range from polyolefin films, like PE and PP, often used in multilayers for thermal shutdown, to ceramic-coated films for enhanced thermal resistance and safety. Critical design parameters include porosity and permeability for ion transport, puncture and tensile strength for mechanical integrity, and managing thermal shrinkage for safety. Ultimately, optimizing these parameters requires a delicate balance between safety, performance, and cost, making the separator a complex and critical component in Li-ion battery design.